Ever stared at a mountain of data and felt that familiar wave of where on earth do I even begin?
Oh, yeah.
Especially if you're, just starting out with data analysis in Python, it can feel like being dropped in the deep end.
Totally.
Well, you're in the right place. Welcome to the deep dive where we take those dense guides and articles and try to pull out the really useful stuff. Today, we're laser focused on demystifying those initial steps of exploratory data analysis, or EDA, using Python.
Right.
Think of this as your essential toolkit for getting your bearings with any new data set.
Exactly. Forget trying to run before you can walk, right?
Yeah.
This deep dive is all about understanding your data from the ground up using Python.
Okay.
We've sifted through a range of practical guides that really emphasize how to do EDA, the actual Python commands you'll use.
The practical side.
Yeah, the practical side. Our mission today is simple: to give you, someone perhaps new to the world of development and data, a solid grasp of EDA in Python. We're going to show you how to perform those crucial first checks and start to see the structure and relationships within your data without getting lost in a maze of jargon.
Okay, so let's get right to it. Why can't we just, throw our data into Python and start making charts or building models straight away? What's the big deal with this EDA thing?
That's a really good question. Imagine you're meeting someone for the first time. You wouldn't immediately start making assumptions about their life story, would you?
No, probably not.
You try to understand their background, their experiences, right? EDA is very similar. It's about getting to know your data before you start trying to analyze it deeply.
Okay.
It helps us make sure the data is actually, clean and coherent before we even think about more advanced stuff.
Right, before the fancy techniques.
Exactly. And these initial EDA steps, they're great because they don't actually change your original data at all. Instead, they help you spot potential problems that could really mess up your later analysis. Things like missing information, repeated entries, or those weird values that just don't seem to fit.
So it's like a preliminary investigation, making sure the data we're working with is actually reliable before we build anything on top of it.
Precisely. That's a great way to put it. And it goes beyond just finding problems. EDA also gives you those early, valuable insights into the data's structure and relationships.
Oh, so?
Well, you start to see how different pieces of information connect, what patterns might be emerging, and maybe even what new questions you should be asking about your data. Like, I remember once we were looking at customer feedback data, and just a simple count of the different categories revealed a misspelling.
Oh, really?
Yeah, just a typo in one of them that was making a particular complaint type seem much less frequent than it actually was. That basic EDA step saved us from drawing totally wrong conclusions.
That's a great example. Okay, so how do we actually start this getting to know you process with Python? I keep hearing about this Pandas library. Is that the place to start?
You've hit on the key tool, definitely. Pandas is pretty much the go-to library in Python for working with and analyzing data.
Right.
Usually the very first thing you'll do is load your data set. A really common format you'll bump into is the CSV file, comma-separated values.
Okay.
And Pandas makes this super easy with a function called pd.rebot.retsv.
pd.reretsv. Ooh, simple enough.
Yeah. Once you load that file, it gets stored in something called a data frame. Think of it like a table. And that data frame is where the fun begins with the initial inspection.
Right, a data frame.
Yeah.
So what are the absolute must-know commands for someone just starting out, to get a first look at this data frame?
Okay, there are a few essential ones. First up, there's shape.
.shape.
Yep, shape. This tells you the shape of the data set.
Okay.
Basically the number of rows and columns.
Yep.
Think of each row as one observation or data point, and each column is a different feature or piece of information about that observation.
Gotcha.
So you might see an output like, say, 1005. That just means your data set has 1,000 rows and 5 columns.
Simple rows and columns. What else?
Next up are head n and tail.
Head, tail?
Yeah. Head lets you see the first n rows, and tail lets you see the last n rows of your data frame.
Oh.
If you just type head or .tail without putting a number in the parentheses, it defaults to showing you the first and last 5 rows.
Oh, handy.
Yeah, it gives you an immediate glimpse of the data, helps you understand how it's structured, what kind of info is in each column, and maybe spot any obvious formatting issues right off the bat.
Okay, so head and tail are like a quick preview. What else can we use for this initial peek?
Then you have columns. This simply gives you a list of all the names of your features, the column headers.
Just the names.
Yep. Useful to make sure you've loaded the right data and see all the variables you're working with. After that, a really, really informative one is .info.
.info.
.info. This function gives you a summary of your data frame. It tells you the total number of entries, which is just the number of rows.
Okay.
The data type of each column, like is it numbers, text, dates,
Yeah.
and crucially, how many non-null values are in each column.
Non-null. So the actual filled-in data.
Exactly. The actual filled-in pieces of information. This immediately flags any missing data. .info. Also tells you roughly how much memory your data frame is using.
Useful.
Very. And for a more direct look at just the data types, you can use the .dtypes attribute.
.dtypes. Okay.
And finally, if you want to see just a random selection of rows, which can be surprisingly helpful for spotting weird entries or missing values scattered around,
Yeah.
you can use .sample_n, where n is just the number of random rows you want to grab.
Got it. So shape, .head, .tail, .columns, .info, .dtypes, .sample. That's a good starting toolkit.
Definitely a solid start.
So we've loaded our data, gotten a good initial feel for it with these commands. What comes next in making sure our data is up to snuff? The sources mention data sanity checks. That sounds important.
Absolutely. It's the next logical step. Now that we have a basic idea of what our data looks like, we need to start checking its quality, its integrity.
Right.
The main goal of these sanity checks is to find any missing values, duplicate entries, or other kinds of issues that could, compromise our results later on. And we want to do this before we start any serious analysis.
Okay, missing values and duplicates. Those sound like big ones we'd want to catch early. How do we find those in Python? Is it complicated?
Not at all. Pandas makes it pretty easy. For missing values, there's a really handy method chain.
Yeah.
Be@iis
Sum.
bowl.sum.
Okay.
Yeah. When you run that, it goes through your whole data frame, column by column, and just tells you the total count of missing values in each one.
Oh, nice. Quick overview of the gaps.
Yeah, exactly. And finding duplicates is just as straightforward. You can use df.duplicated.sum.
Well,
Yep, that gives you the total number of rows that are exact copies of other rows in your data set.
easy enough. What about other kinds of data integrity issues? What else should a beginner be looking for at this stage?
Well, that can cover a few things. One important aspect is understanding the variety of values within each column.
Oh.
You can use the unique method on a specific column. That just counts the number of unique or distinct values it contains.
So, like, if you had a country column, it tells you how many different countries are listed.
Precisely. And this can be super useful for categorical columns. If you see an unexpectedly high number of unique values in a category you thought should be pretty standard.
Like state having 70 unique values instead of 50.
Exactly. That might point to typos or different ways of writing the same thing, inconsistencies.
Okay.
You can even check this quickly for all your columns using a little loop. Something like for column in data.columns.print. Unique values in datacolumn.unique.
Ah, neat trick.
Yeah. Beyond just the count of unique values, you might also want to know what the most frequent value is in a column.
Okay.
You can find this using the .mode method.
.mode.
And to see how often that most frequent value actually shows up, you can use .valueCounts. .iloc0.
.value counts. .iloc0.
Okay, .value counts gives you the counts of all unique values, and .iloc0 just grabs the count for the top one.
Got it.
And finally, you can also check the total number of non-missing entries in a column using .dropinternet.counts, another way to see how complete each column is.
So after running these initial checks missing, duplicates, uniqueness, mode, we should have a much clearer picture of any potential data quality problems, right?
Exactly. You'll have a much better sense of the data's overall health.
Okay. What's the next phase in actually, digging into the data itself? The sources talk about univariate analysis. That sounds like we're looking at one variable at a time.
That's precisely it. Univariate analysis is where we focus on examining each individual variable in our data set by itself. Uni, meaning one, variate, meaning variable.
Okay, one at a time.
Yep. The main goal here is to understand the distribution of each feature, how its values are spread out, and identify any initial patterns, unusual values, or potential issues within just that single variable. It's really a fundamental step.
Right. So how do we analyze a single numerical feature, like age or price or something like that? What tools does Python offer?
For numerical features, visualizing the data is incredibly helpful. One of the most common techniques is using histograms.
Histograms. Okay, I've seen those.
Yeah, they show you the frequency of values within certain ranges or bins. In Pandas, you can actually generate histograms for all your numerical columns at once using df.hist.
Oh, all at once. That's efficient.
Very. And you can customize them quite a bit, too. Like the sources show an example. Data.hisFigSize bins 20 edge color black. That controls the plot size, the number of bins, and adds an edge to the bars to make them clear.
So the histogram gives you the shape of the data's distribution.
Exactly. You can see if it's roughly bell-shaped, like a normal distribution, or if it's skewed to one side or maybe has multiple peaks. Really useful first look.
Okay, histograms to see the shape. What other visual aids are good for looking at single numerical features?
Box plots are another really powerful visualization.
Box plots, right. Those show the median and quartiles.
Yep. They give you a nice summary of the distribution. The median, the quartiles, which divide the data into 4 equal parts, and the overall range. And importantly, box plots are great for highlighting potential outliers.
Ah, yeah, outliers, those extreme values.
Exactly. Values that fall way outside the main chunk of the data. You can create box plots easily using libraries like Seaborn. It often makes nicer looking plots than the basic ones.
Seaborn, okay.
Our sources even mention you can make them horizontal using vert-false in SNS.boxplot sometimes, which can be easier to read.
Horizontal box plots. Interesting. So visuals are key. What about just getting the raw numbers?
Absolutely. Beyond visuals, you'll definitely want to look at descriptive statistics. Pandas has the .describe method for this.
.describe?
Describe. It calculates key summary stats for all your numerical columns automatically. Things like the mean, average, median, middle value, standard deviation, spread, min, max, and various percentiles.
All in one command.
Yep. And a useful tip, adding T at the end, like data.describe, T transposes the output table. It flips rows and columns, which often makes it easier to read, especially if you have a lot of features.
Describe T. Good tip. Any other plots for numerical data?
Well, you might also encounter density plots, sometimes called KDE plots, kernel density estimate plots. You can make those with SNS.kdplot. They basically provide a smooth version of the histogram, showing the distribution shape in a continuous way.
Okay. So histograms, box plots, .describe, and maybe density plots for understanding individual numerical features. What about categorical features, like product category or yes-no answers? How do we analyze those on their own?
Good question. For categorical features, we're mostly interested in how frequent each category is. How many times does each option appear?
Right.
Bar plots are the standard visualization here. Really simple. You can create them using dfcolumn.valuecounts.plot. Cot, bar.
It's okay. Value counts and then plot.
Exactly. Or you could use Seaborn again with sns.countplot. Both will show you bars representing the count for each category. Super easy to see the most common and least common ones.
Can you order them? Like most frequent first?
Yeah, using .valuecounts.index can help with ordering them if you need to.
Cool. And besides plots?
Definitely look at the frequency tables directly. The value counts method itself gives you the raw counts for each category.
It's just the number.
Just the numbers. And if you want to see the proportion or percentage of each category, which is often really useful for context, you can use .valueCounts, normalized true.
Normalized true gives percentages. Got it.
Yep. That's great for understanding the balance or imbalance between categories.
Okay, we've explored our variables one by one. Univariate analysis. Now, what if we want to start seeing how two variables interact? The sources mention bivariate analysis.
Yes, bivariate analysis is the logical next step. Now we start investigating relationships between two variables at a time, bi meaning two.
Right.
This helps us understand if there are any associations, correlations, or patterns between pairs of features.
What are some common ways to analyze the relationship between two numerical features, like maybe age and income?
Scatter plots are fundamental for this.
Yeah.
Really common.
Scatter plots, okay, X and Y axis.
Exactly. You can create them using sns.scatterplot from Seaborn or the basic plt.scatter from Matplotlib. You plot one numerical variable on the x-axis, the other on the y-axis, and each point on the plot represents one row, one observation from your data.
And what are we looking for?
You're looking for patterns. Does one variable tend to go up when the other goes up? That might suggest a positive correlation. Or does one go down as the other goes up? Negative correlation. Yeah. Or maybe there's no obvious pattern, or perhaps you see clusters of points.
Okay, visual inspection for trends.
Right. And if you want a quick overview of the relationships between multiple numerical features all at once, pair plots are awesome. You generate them with sns.pairplot. Creates this grid of scatter plots showing the relationship between every possible pair of numerical columns in your data set. Plus, it usually puts histograms or density plots on the diagonal.
Wow, like a dashboard of relationships?
Kind of, yeah. It's great for quick exploration. Lastly, To get an actual number that measures the linear relationship between two numerical features, you calculate the correlation coefficient.
The correlation number.
Yep. You get this easily using df.core. This gives you a table, a correlation matrix, where the values range from -1.
Perfect negative relationship.
Right, to +1.
Perfect positive.
Perfect positive linear relationship. And a value near 0 means little to no linear relationship. It's important to remember it measures linear correlation.
Okay. And can we visualize that matrix? All those numbers can be a lot to take in.
Absolutely. Heat maps are perfect for that. You use sns.heatmap and feed it the output of df.couture. It colors the cells based on the correlation value, making it really easy to spot strong positive or negative relationships visually.
sns.heatmap.
Nice. Scatter plots, pair plots, correlation matrices. That gives us some good tools for numerical pairs. What about when we have categorical variables involved? Or maybe one numerical and one categorical?
That's a great point. Well, our focus today, especially for beginners, is on these foundational techniques, and the sources didn't dive super deep into mixed-type bivariate analysis.
Right.
It's definitely a crucial next step. For instance, you might use box plots again, but this time to compare the distribution of a numerical variable across the different categories of a categorical variable.
Like comparing average income across different education levels using box plots.
Exactly like that. Or you could use grouped bar charts or things called contingency tables to look at the relationship between two categorical variables.
These are really powerful techniques and definitely something we can explore in more detail in future deep dives.
Okay, that sounds like something to look forward to. Now, earlier we touched on outliers. We mentioned spotting them in box plots. But what do we actually do once we find them? We can't just ignore them, can we?
Good question. So, yeah, an outlier is basically a data point that lies way out in the extremes compared to the rest of the data. Unusually high or low.
Right.
They can pop up for lots of reasons, maybe a typo during data entry, a glitch in a sensor, or sometimes they're actually real, just rare events.
Like a billionaire's income in a neighborhood survey.
Exactly. And it's important to identify them because they can sometimes really skew your overall analysis, like pulling the average way up or down, and maybe lead you to the wrong conclusions.
So we find these potential outliers. What's the game plan? Just delete them?
Not necessarily. The sources really emphasize that you need a plan, and the best approach depends heavily on the context, on why you think it's an outlier.
Okay, so options.
Well, one option is removal, yeah. Especially if you're pretty sure it's just a flat-out error, like someone typed an age of 200.
Right, that's probably wrong.
Probably. Another approach is transformation. Sometimes applying a mathematical function, like taking the logarithm, can squish the range and make those extreme values less impactful without deleting them.
Transformation.
But, and this is crucial, sometimes you absolutely should not remove outliers. They might represent real important signals.
Like your fraud detection example.
Exactly. In fraud detection, that huge transaction might be the most important data point. Or in medical research, an unusual patient response might be key.
So you need to think carefully.
You absolutely do. The key takeaway is to have a review process. Investigate the outliers. Understand why they might be there before you decide whether to remove them, transform them, or keep them as is. Don't just blindly delete things.
That makes a lot of sense. Preserve data integrity. This has been a fantastic overview of these initial EDA steps with Python. It's actually amazing how much you can learn about your data just with these fundamental checks and plots.
Absolutely. It's the foundation. And as you get more comfortable, you'll find Python is incredibly powerful for automating a lot of this.
Automating? How so?
Well, our sources even showed examples of writing your own Python functions to do things like automatically calculate statistics and generate standard plots, KDEs, box plots, histograms for all your numerical columns.
Oh, wow.
Or functions to analyze category frequencies and find the mode for all your categorical columns. Even functions for some basic bivariate analysis, like comparing numerical data across categories, or doing statistical tests like chi-square for relationships between categorical variables.
So you can build your own EDA toolkit.
You can.
Yeah.
And beyond writing your own code, there are also brilliant libraries out there like Pandas profiling or SweetViz.
Pandas profile.
Yeah, with just like 1 or 2 lines of code, these libraries can automatically generate really comprehensive, interactive HTML reports summarizing your entire dataset distributions, mything values, correlations, potential issues. They do a huge chunk of the initial EDA for you.
Whoa. Okay, those sound incredibly useful, especially once you know what you're looking at.
They really are. Great time savers.
So for anyone listening who's new to data analysis in Python, may be feeling a bit overwhelmed by that mountain of data we talked about, what's the single most important thing to take away from this deep dive?
I think the most important takeaway is that exploratory data analysis isn't just some preliminary chore you have to get through. It's an absolutely essential first step, especially when you're starting out.
It's foundational.
It is. By systematically doing these initial checks, these visualizations in Python, you build understanding. You avoid common mistakes, you uncover valuable insights early, and you start asking much smarter, more informed questions about your data. You're laying that solid foundation before you try to build anything complicated on top.
So, if you're that new developer facing a data set, the advice is take a deep breath, fire up Python, load your data with Pandas, and just start exploring. Use those initial inspection commands like .head, .info, run your sanity checks, check for missing data, duplicates, then dig into univariate analysis, look at variables one by one with histograms, and .describe, maybe try some bivariate scatter plots.
Exactly. Get to know your data.
You might really be surprised by the interesting things you discover lurking just beneath the surface once you actually start to explore it, right?
Absolutely. It's often full of surprises. And as you get more comfortable with these basics, start thinking about what's next. What specific parts of EDA do you want to understand better?
Yeah.
Because future deep dives could definitely go into more advanced techniques, maybe really focus on data cleaning strategies, or dive deep into specific visualization libraries like Seaborn or Matplotlib. There's always more to learn.
Sounds like a plan. Plenty more to explore in the world of data.